Welcome back. The second part is going to be much shorter. I just want to go through the last few details. I keep machines and applications in another video, so it's going to be easier to manage. For this week, I would say getting to this point would be definitely enough. So start to play around with Rhino, have an idea of how lasercut works, and next week we will see the rest, get into the first exercise, and eventually talk about the tutorial as well. So we stopped with the previous video here. This is another interesting application of cutting different materials and snaps them together into a single piece. This is a very easy way, very robust, very resistant even over time, to get different colors, different materials without painting things. It also leaves a very clean, very precise mark. It's not widely used, but it's still an interesting thing in my opinion. And if you want to create resistant parts, it's easier to cut different colors of plexiglass, for instance, instead of paint over the same kind of plexiglass. Now, it's not necessarily an interesting application, as I said before, but sometimes could be, fascinating to explore different things. If you will play around with sensors, capacitive sensors, interactive objects, this is very nice to create interfaces that people can touch, interfaces with LEDs underneath, transparent parts. So it's really fascinating, the result you get. Now, another fun application is to create partial cuts, or better, dot line cut through materials that can be easily bent, like paper. So this is a pretty complex object that you can see here, but a very fun application is actually this. There is a pretty fun software to use called the Pepakura, and well, let's use Google. So Pepakura is a software that transforms a 3D file into patches, pieces of paper that can be glued together. So from the most simple one, okay, to pretty intricate one. The masks are very commonly developed this way, and these are just, pieces, stripes of paper that you glue together. Now to get here, you have to be very patient, but if you have to create a big object, if you have to create shapes or check the dimension of something, this is definitely something you can try. A good friend of mine is into cosplaying, and he is great in developing these objects. He made a lot of costumes and masks and tools, just designing things in 3D, using Pepakura to create pieces of paper, glue them together, spread layers of resin on top, and getting objects that would cost much more using different technologies, even 3D printing them. So if you want, you can, have fun with it, explore a bit. In general, the point is that Pepakura is designed to give you this. Usually you print it on paper, and you just cut them with scissors and glue them together. That's definitely not the most efficient way. With laser cutter, you can easily do that almost automatically with the machine. So this is one example, but similar approach can be used for plastic as well, in particular polypropylene. I'm sure you used it in the past. You might not know that the name is polypropylene, but you definitely know the material. So polypropylene is a very flexible, very strong kind of plastic. If you cut it, but not going through the entire material, so it's just a very light cut, it's just a very it's just making the surface a bit thinner in that point. You can fold it and it's really resistant. So just to give you an idea, we spoke before about the lens. We have to go back to lenses and focusing the laser in a while, but in general, if you have a very focused laser, you concentrate a lot of energy in that. What happens is that you have your material and the laser is burning away a very small amount of material, and that cuts the piece in two parts. Playing with energy, speed, and the focus itself, you can create a completely different shape of the cut that is more like a bump. So this is just reducing the thickness of the material in this area, and this will work as a hinge. So it's very easy to do it. There are a few tricks. You have to do a bit of experiments, but you can easily make something that is actually flexible. Now, about flexibility, you can use this as hinges in moving objects, in particular with paper, that it's great on that perspective. So this is a pretty old Kickstarter, but I really liked it. So I kept it as a reference.
Kinetic creatures are walking cardboard animals that you build from a tab and slot kit. There's Ellie, Rory, and Gino.
Each creature takes a complex mechanical linkage and makes it accessible through an easy assembly and a charismatic form. The kinetic creatures come alive with a simple mechanical movement. They can also walk on their own with a gear kit. The insides are an open platform for your own inventions too, with Lego, Arduino, and more. This is our gear assembly, which you can build from a kit. When you receive your kinetic creature, all of the building instructions will be on our website, where we'll walk you through the process of building your animal step by step. Hi, I'm Lucas.
Hi, I'm Alyssa.
I'm an industrial designer,
I'm an artist and art teacher.
and our project is called Kinetic Creature.
We are interested in the act of making.
I would say that's enough. You can see how it worked. Basically, this was just...
As an art teacher, I'll use the animals in my class.
This was just a very simple project, basically a laser cut cardboard. When the cuts don't go through the entire object, then you can use the last layer as a hinge. The system is very simple and pretty robust, actually. So just to recap, what can you cut with a laser cutter and what you cannot cut? Well, the range of materials is very wide. You go from very well-known materials to be used with these machines, like plexiglass or plywood or wood, cardboards, paper, rubber, leather, fabric. Keep in mind that rubber and leather in particular could be very smelly. So when you laser cut leather, the smell you get, unfortunately, is the one you get when you burn something that was alive. So it's really disgusting, and it's much easier to use synthetic leather, beside the fact that you don't kill anybody to actually get it. The only problem you could have with synthetic leather is that sometimes it's made with PVC. PVC is a particular kind of plastic that you definitely shouldn't cut with a laser. So PVC is basically a very common plastic. It could be soft and rubbery, it could be hard and rigid. It's usually transparent, but you can find it in colors and not transparent as well. When you burn this, it releases acid. So a lot of machines have decent filters, so the vapors will not get into the environment. Not all of them. But the main problem is, in this case, you ruin the machine as well. So it's not just a matter of don't release gases, it's also a matter of destroying your machine. Polycarbonate is another tricky one. Amazing materials, super resistant, transparent, beautiful. Very similar to plexiglass actually. But when you burn polycarbonate, you get dioxin, and that's a toxic gas, and you shouldn't be around it for any reason. So when you buy plastic, in particular transparent plastic, you have to be sure that it's plexiglass. Plexiglass is a commercial name. The material is PMMA, polymethyl methacrylate. It's the chemical formula of the material. Usually it's just written as PMMA. Sometimes you find it as acrylic slab, sometimes you find it as plexiglass. But keep in mind to double check every time you laser cut plastic in particular. And synthetic leather is actually plastic. Some of the synthetic fabrics are actually plastic. So double check what you get. If you don't know the material, a pretty basic trick, even if not the best one, is to take a small corner of the material, fabric, leather, or plastic, and burn it. Burn it with a lighter. If you get a brownish smoke or a brownish finishing or surface after you burned it, that's definitely not a good sign. So if you have any doubt, it's better to be safe than sorry. Don't cut something that you're not sure about. Now, glass and metal is not necessarily something you can't laser cut. Glass can be laser cut with special machines, metal as well. The point is, both of these materials require special machines. They require special machines and they are not available easily in fab labs, for instance. The typical laser cut from in a fab lab or in a university lab is a CO2 low power laser cutter. Low power means less than 120 or 160 watts. Those machines can't cut metal nor glass. So it's easy to find suppliers for these materials. My suggestion is, even when you develop a project, if you really need those kind of things, develop it and test it and prototype it with a piece of paper, thin layers of cardboard, plywood. When you get the shape, when you're sure about what you're doing, then you order pieces in metal cut from suppliers outside of the lab. Last point, thick materials. Now, this is a tricky thing, and it goes back to the shape of the laser cutter. So if you remember the first slide in the last video, you get something like this. That was the nozzle of the laser cutter, and you got a lens inside. The laser was getting in from the top. The lens was focusing the laser on the piece, and then you had the piece, and here you had your cut. Okay, so this is the part that it's still one piece, and here you have the cut. Now, to simplify this, we can say we have a laser source, we have a lens. The laser source is focused by the lens. Now, just to be a bit more clear, let's have the laser yellow. Now, because of the way it's made, the lens, and this is done in purpose actually, the laser is not focusing on a single point, but it's creating a sort of intersection in different points. Okay, the overall shape is this. Okay, so why the lens is creating this weird shape instead of a nice, neat double cone shape? Well, because the double cone is focused only in one point. And that's the only spot where you are at the right focus. That means that it would be perfect to cut zero thickness materials, and that's definitely not what we work with. In this case, what you actually get is an area of almost parallel cut. So this shape is almost cylindrical, and you have a maximum thickness that is related to the lens. So of course I can cut things that are thicker than this, but the thicker it is, the less focused it will be. Now, about focus, a lens is focusing the energy, and the energy is distributed in a Gaussian curve. So let's say that this is the center, okay, the virtual perfect spot. The energy I distribute is a curve like this, okay? If the laser is not at focus, the curve is going to be much larger. So I warm up a large area of the material, all this area here, and maybe I'm burning a bit more here, or maybe not, but in general I will not be able to cut anything in this case. Now on the opposite, on the opposite side, if I focus very well the laser, the curve is going to be very narrow, and in that case this part here will be enough to actually cut away the material, or maybe not exactly that part, but probably more a very narrow area here. Okay, so because of this, combined to the shape of the laser cut when it's focused, I have a certain set of limitation in what I can cut. We already see that too thick materials could be complex to cut. So when I have a very thick material, the cone will be in focus for a certain part, but then out of focus for the rest. And therefore the final result will be very poor. Now the amount of, let's say, optimal focused part is proportional to the length of the focus. That's how it's called. So let's try to be a bit more precise. Let's say that this is the surface of my piece. Very short lens will focus a very narrow cone, but this is gonna be also opening up quite quickly. Longer lenses will focus a bit less, but for a longer time, and so on. So based on the thickness, on the length of the lens, it's possible to decide if I want to have a pretty long, quite wide laser ray or a very short, pretty narrow laser ray. This, of course, starting from the same kind of lens, from the same kind of laser and source. Now, in this case, I'm focusing the energy much more. So this is going to be faster, more precise, more clean with a smaller curve, but it will work only on not super thick materials. This is going to be slower with a more rough finishing, less clean, wider, so a larger curve, but I can probably cut thicker materials as well. So it's a trade-off. It's really a matter of choosing what you want. And again, you can change the lens eventually if you want to. This is just to explain to you why it's such a big deal to cut thick materials. Quickly, when you engrave you can use the laser to engrave as well. That means you have a set of vectors. The machine is set up to move fast enough to don't actually burn away the entire material, but just to score something on top of it. If you have doubts on how to remember the ratio between the power and the time, there is a pretty fun trick. Now, think about this as a laser. If you have a surface that you want to cut and a laser, if it moves fast enough, it's gonna be just enough to warm up the surface, so eventually to leave a small mark on the surface. But if it goes slower, well, I'm not gonna show you, but trust me, it's gonna go through. So every time you have a doubt on how to set up the machine, keep in mind this. You go deeper if you go slower, if you don't change the power, of course. I wouldn't do the same trick with a big fire or putting my hands over a welder or something like that. So that's the concept of engraving. It's just not giving enough time or not giving enough energy to the material to burn away completely. So why is this useful? Well, first of all, you can use it to engrave the surface of your objects. This is great for a visual impact, but also you can actually get a bit deep inside the material, so you can fill the gaps with resins. You can get very neat, very nice finishing. So for animations, for surfacing, for interfaces, for pictures and decoration, this is great. The final result is really beautiful. Now, to do this, you need closed path. So while a single line can be a vector like this, if you want to get to this kind of engraving in which an area is completely in field, well, at that point you really need to close the vectors and the path to allow the laser to understand what to engrave and what to don't touch. In theory, well, in practice as well, actually, with lasers you can engrave pictures on the material. Keep in mind that when you print a black and white picture or color picture on a piece of paper, you get an amazing resolution. You have 4, sometimes 6 different colors, you have super tiny pixels, and you have a range that goes from perfectly white to completely black. When you engrave pictures on a piece of wood, you don't have this depth of color. The wood is brownish, even if it's very light, and when you engrave it, it's not gonna get black, it's gonna get darker. So if you have a wide range of gray, if you have a very complex picture, usually when you engrave it, you don't get a good result. You just get something pretty flat. There is a trick to improve the quality of the pictures when you laser cut them, and it's to use dithering. So it's a pretty old filter used for very old computers and very old screens, but it's basically a way to represent grayscales in black and white only. If you filter the pictures this way, you can easily increase the perception of the different colors instead of just engraving it this way. There are a bunch of other tricks, but at the moment I don't think it's fundamental to go through all of this. So what can you engrave compared to what you can cut? Well, you can engrave basically everything you can cut, so it's pretty simple, but you have a couple of extra things that can be treated this way. Metals, for instance, when they are varnished or anodized, can be engraved because the laser will not be powerful enough to go through the metal, but it's definitely enough to change the color and the appearance of either the thin layer of oxide that creates the anodized effect, or to take away the varnish on top of the metal. Now, glass, stone and ceramic, you can leave marks on those. It's very hard to control, very hard to get a good result. But if you want to play around with that, you're more than welcome. Just to give you an example, because it's pretty well known and pretty fun, is what a lot of people did to their computers. Maybe written in the proper way. So what you see here is actually a picture that someone engraved with a laser on the back of their computer. The resolution you get is amazing, of course, and if you want to try, you're welcome. I suggest you to pay a lot of attention to this. So no one actually went over the apple in this specific case, because this is not metal, this is plastic. The laser will go through it. So if you want to try, feel free, do it carefully. Okay, that's it about engraving and laser cutting. Next time we'll talk about machines and have some examples. Bye guys.